Hello everybody, in this lecture we will be solving 1999 USAMO problem number 6. It's a geometry problem. We're given an isosceles trapezoid ABCD where AB is parallel to CD. So let me go ahead and draw this trapezoid. So we have a configuration like that. So we know that this trapezoid is isosceles, so probably I should do it a little bit like that. And I will just delete the extra part. Okay, so this is A, B, C, D. And furthermore, we would like to inscribe a circle inside triangle BCD. Now that's a challenge, obviously. So if we draw this triangle BCD, so the in circle of this would be, okay, so something like that. I hope my picture is relevant. Okay, so something like that, I would say. Those are the three touch points. Okay, good. And this circle is called omega, and it is tangent to CD actually at a point called E. At a point E here. Okay, so let F be a point on the internal angle bisector of DAC. Okay, so we are talking about the angle bisector here. Yes, so we have the angle DAC and we want an angle bisector. So probably something like that, I would say. Yeah, my drawing, but okay. And well, it is somewhere here such that EF is perpendicular to CD. So EF is perpendicular to CD, suggesting that F is right here. F. So this is an angle bisector, and EF is perpendicular to DC. Let the circumscribed circle of triangle ACF. Okay, so that's a challenge already. Let me use another color, I guess. Let's use the red color. I need to draw the circumcircle of A, C, this point here, and F. Yeah, so it's kind of, I'm just drawing a random circle here, actually. So like that, and something like that. Okay, and we are told that this this circle will meet the line CD. So CD would be this line here. At this point here, G, and we need to show that AFG is actually an isosceles triangle. So this triangle here, AFG, this one is isosceles. So in fact, what I will do is I would like to show that angle FGA is equal to angle FAG. So that would immediately give the desired results. AFG would become isosceles as a result. So how to attack this problem? Let me just remove some portion of this circle here, which okay. So how to attack the problem, and especially the given property, right? So we are told that this is an isosceles trapezoid where AD is equal to BC, and I'm curious about the point F here. So what is the significance of this point, right? I claim that strangely probably that F is the AX center of, let me write that down. So F is, so that's only a claim obviously. So claim F is the AX center of triangle ADC. Why would that be? The reason lies in the fact that AD is equal to BC, but also two triangles are congruent triangles, namely BCD. So triangle BCD is congruent to triangle ADC, I should say, ADC. And as a result, their in circles would be identical. So so you would have an identical size in circle here on the other side, right? So because the two triangles are congruent. But then that gets me thinking, namely that the touch point of this circle, let's call it point E prime. So it is, well, due to this nice symmetry, DE prime here is equal to EC, but that's exactly the configuration of Yu-Feizhao's lemma, right? Namely that that the in circle and the X circle are in dilation, and so if I take the point diametrically opposite E prime here, and I don't know, let's call it E double prime, I guess. But the idea is that if I had to draw the line AE double prime, it would hit the point E here, and moreover, because the center of the in circle here of this circle is, let's call it I prime, and F would be collinear. So therefore, what I'm saying is that A is the center of a dilation of a homotety that would take the black in circle here to the X circle, to center that point F. So let me go ahead and try to draw that circle. Yeah, let's use the green color, I guess. So it would be a circle like that. It would be tangent here. It would, also be tangent to this side here. So something like that. And let me just clear this mess a little bit. But yeah, so the idea is though clear, I guess, right? So so the symmetry here, the fact that DE prime is equal to EC, implied immediately that F is the center of the AX circle of triangle ADC. So I highly recommend you read the discussion about the diameter of the in circle, like in this case E prime, E double prime, and how E double prime and E double prime and E are becoming collinear. Okay, so now that's a huge improvement. So let me actually make a couple of changes here. So this point here is the point C, as you remember. Let's call this other tangency point as X. So it is the tangency point between the green circle, the X circle, and the line AC. And as a result, EC is equal to CX, right? So X is probably somewhere here. So this is a 90-degree angle here. And let me also make note here that EC is equal to CX due to the tangencies. Now the rest of the problem, let me also connect FC as well. So in fact, let me also make this additional note that triangle FEC is in fact congruent to triangle FXC. So the rest of the problem is basically chasing relevant angles. So if you start with GAF, I'm talking about this angle here. So the angle GAF, let me probably also write it here, angle GAF is obviously subtending the arc GF here, but this arc is also subtended by another angle, namely angle GCF. But notice earlier we claimed these two triangles are congruent, and which is obvious because you have the radii of the green circle here and these two lines are equal and you have 90-degree angles, so side angle side congruency. But anyhow, so GCF, which is this angle here, is congruent to or equivalent to XCF, angle XCF. But now notice that XCF is equal to 180 degrees minus FCA, right? So because so they are supplementary angles, so this is equal to 180 degrees minus FCA, angle FCA. Now notice notice that GACF is a cyclic quadrilateral. GACF CF is cyclic, and as a result, FCA, which is an opposite to the angle FGA, so this thing is equal to, namely, FGA, right? Does that make sense? Because you have 4-point cyclic, this is a condition of being cyclic, right? And that's boom, so we have the desired result. So we have found that FGAF is in fact equal to FGA, and as a result, FG is equal to FA, and this triangle FAG is an isosceles triangle, and that solves the problem. Hope to see you in our next video.